The final topic of this notebook is Section 6, Exponential Models 2. As the name suggests, this is a continuation of Section 2, Exponential Models 1. There, we concentrated upon three types of applications of exponential functions. Number one, compound interest model, which is used in finance and especially personal finance, and accounting. Number two, logistic model, which has really a variety of applications in life sciences and social and behavioral sciences. For example, bacteria growth model or ecosystem model belong to biology. Ecosystems, to a certain degree, may belong to environmental sciences too. And for example, rumors spreading around in social network, for example, belong to social and behavioral sciences. It has a lot of applications. Number three, radioactive decay model, which is most definitely physics and engineering type of examples. This one doesn't really have a lot of applications, but this one is really quantitative. As a matter of fact, the compound interest model here is actually not precise equality. This should be approximate equality. The reason is because the interest rate does not stay constant. Logistic model, of course, cannot be precisely equal because of all kind of other factors. Radioactive decay model, on the other hand, we have precise equalities because it's coming from laws of physics, which is actually directly related to probability models in mathematics. So this one may have most narrow applications, but quantitatively the most precise. So there are some trade-off one way or the other. That, and for a variety of other reasons, we are going to concentrate upon these two applications, logistic model and radioactive decay model. Take those two and let's look at those two in more detail, especially in the viewpoint of exponential and logarithmic equations. That's what we are trying to do in section 6. Here's an example. A herd of deer is introduced onto an island. Initial population is 500, and it is estimated that the long-term sustainable population is 2,000. So that's the mature population, and that goes to the numerator. Why? When t is really big and approaches infinity, then what do we have? E to the negative 0.044 times t. When t is really big, we have e to the negative infinity, so that's pretty close to 0. E to the negative infinity times 3, so it's basically 3 times 0. So highlighted part here in this formulation is 0. What do we get in the end? 2,000 over 1. That's how we get mature population for t really big. Now, this is a kind of problem we used to do early on in section 2. Estimate the number of deer population after 1 year, 20 years, and 50 years. What do? Just plug in t equals to 1, t equals to 20, t equals to 50. Just run your calculator, and then you have the answers. Those kind of things are a bit too trivial. And let's go over to the next step. This time, let's set up an equation and solve for t. How many years later does the population reach 1,500 individuals, which means P of t is equal to 1,500. So this expression has to be equal to 1,500, and we have to find out t value, and that's an equation, that's an exponential equation. And here's the solution. So P of t is 1,500, so let me expand the font. Okay, so we have an exponential equation, and what we need to do is solve for e to this part, the exponential. Solve for that, and then in the end, take the log of both sides, and then you're going to be able to find out t value. Here we go. Number one, Move the denominator to the other side. Break out the parentheses. And eventually we are solving for the exponential part. Subtract away 15, divide away 45, and we have e to the negative 0.04 is 1/9. Okay, we are ready. We have a number in the left hand side and we have an exponential in the right hand side. So all we have to do is to take the log of both sides. And we have log of 1/9 is equal to exponential of negative 0.04t. And exponential and log cancel each other out, so we only have negative 0.04t. So divide away negative 0.04, and what do we get? Log of 1/9 over negative 0.04, calculate out, and we have 54 point something. So it's gonna take about 55 years until the population reaches 1,500 individuals according to this model. And where do you use this kind of application? Well, if it is herd of deer, that's a little bit difficult to, well, okay, herd of deer is okay. Introduce herd of deer into Ireland, and then let's suppose target population to allow deer hunting is 1,500, for example. According to this model, you will have to wait 55 years until you can allow deer hunting. I don't know, it depends upon your viewpoint. If you're a hunter, you're going to be disappointed. If you're the other way around, then you're going to be happy that you don't have to hear the gunshot for 55 years. Never mind. Sorry about the stupid joke. How about some other applications? Let's see. A population of a certain fish in a lake. Similar type of example, only different numbers. We have different mature population and different k values and different coefficient there. In the end, we are setting up an equation. This whole thing is equal to 2,500. It's just another exponential equation, and the key is to solve for e to the negative 0.037t, kind of like this, and then take the log of both sides, and so on and so forth. So those kind of things are applications of exponential models for logistic models. Now let's move on to radioactive decay models. The quantity of radioactive materials okay, I don't like 6.3 very much because it's not really related to the real substance. But let's do it. A quantity of radioactive material can be modeled by the following formula, and then 21.2 must be the initial quantity. If you plug in t equals to 0, then we have e to the 0 power, which is equal to 1. So the highlighted part here is 1. So Q of 0 is equal to 21.2. This is initial quantity. Oh, that was the answer for problem A. Quantity after 2 minutes, quantity after 20 minutes, all you have to do is plug in t equals to 2 and t equals to 20, and then run the calculator. You're going to get the answers. How about the next problem? How many minutes later will the remaining quantity be 10 milligrams? What you need to do is set this one equal to 10 and solve for t, which is an exponential equation, another linear exponential equation. So here it is. 21.2 times exponential is equal to 10.0. All we have to do is solve for exponential first, as we have over here, and take the log of both sides, and exponential and log will cancel each other in the left hand side. In the right hand side we have a logarithm of that number, something like that, and then divide away negative 0.07 and run your calculator, and you're gonna get something like this, 10.73 something minutes. and that's the estimated time. Next example is something I like a little bit better, and part of the reason I like it better is not because I like it better is this one is related to a real substance, and as a matter of fact, I actually dug it up and found out all this data. Americium-241 is a radioactive substance used in common household smoke detectors. The radioactive decay of americium-241 can be modeled by the following formula. The reason is because the half-life is 432.2 years. And you can actually find out by going to a web browser and then just Google search or whatever, americium-241, find out Wikipedia or whatever. You can find out the half-life of it, and that's how I found it and then devised this problem. Now here's the question. We are starting with 10 milligrams and estimate the remaining quantity after 20 years, 200 years, and so on. All I have to do is plug in t equals to 20, 200, and so on here and run the calculator. That's too simple. Let's move on to the next part of the problem. The remaining quantity is 7.0 milligrams, which means this whole quantity, where Q0 is 10, has to be equal to 7.0. That's going to be another exponential equation, and you have to solve it. And here's the setup. 10.0 is the initial amount, and then here's the radioactive decay model, and then equal to 7.0. What do we have? We have an exponential equation. Typical technique is the same. Solve for 1/2 to the that thing, and we can do that by dividing away 10. And what do we get? 1/2 to this power is 0.7. We have this equation here in second line. Now what do we do? The first thing I like to do in this kind of situation is to take the natural log of both sides. Log and exponential in this case will not completely cancel out. However, we can still use log rule, which means we can take this power outside, and we have t over 432.2 times log of 1/2. Log of 1/2 may look intimidating, but it's not, because it's just a number. Log of 0.5 is, well, something you can find out if you punch in the calculator, just like log of 0.7. So divide away this log of 0.5 and then flip away this 432.2, and we have this computation here. Let me expand the font a little bit. There. Log of 0.7 over log of 0.5 times 432.2, and this is nothing more than numerical computation that you can do with your calculator. Run it, you're going to get 222 point something. So it'll take about 222 years, 0.4, about 0.4, so 222 and about 5 months. That's going to be your approximate solution. Well, how about the next problem? Again, this kind of problem will be pretty much the same. You can use either one type of exponential decay model, where we have initial quantity and natural exponential to the negative kt, or you can use half-life if half-life is given. Q0, initial quantity times 1/2 t over capital T, where capital T is a half-life. Here half-life is given as 3.4 years. So all I have to do is replace 432.2 in the previous problem by 3.4. And that's basically what I did over here. Initial quantity Q0 is 14.7, and the capital T half-life is 3.4. And we are looking for how much time for 20.0. This is a solution.